Finding out the structure of the atom was one of the most important discoveries ever. But the idea that everything in the universe is made up of tiny little building blocks isn't a new idea. In fact, even the Greeks thought that everything was made up of tiny little spheres. So they were the first ones to come up with a particle model of matter. And in essence, they were right. They weren't completely right, because we know since then we found out atoms are made up of smaller things. J.J. Thomson, however, turn of the century, about 1900, he discovered a particle smaller than an atom, that being the electron. So he deduced that atoms must be made of negative parts, and that's why it's called Thomson's plum pudding model, where the electrons are these kind of plums stuck in a pudding. Rutherford, though, with his alpha scattering experiment, actually found out that all of the positiveness of an atom was concentrated in a very, very small space. And then we have electrons that orbit the outside. Along with Niels Bohr, after that, we've developed a usable model of the atom. And we call it a model because, well, if we get philosophical, no one actually knows what an atom is, no one knows what an electron is, but we can see what effect they have on the world. And so therefore we can model them as little particles like this. But it's worth just keeping in mind that everything that we do in particles is just a way of interpreting the world around us. So Rutherford found that this positive bit of the atom, the nucleus, was very, very, very small compared to the whole atom. Proportionally, if an atom was the size of a football pitch with the electrons as far away as the goal, away from the centre circle, then the nucleus would just be the size of a pea in the centre circle. Very, very small. So most of an atom is in fact empty space. Now, since Rutherford and Bohr's model, we've come some way since then as well, and we figured out that electrons actually exist in probability clouds and things like that, but we're not going to get into that today. This purely particle model of the atom is good enough for now. And that's what science is all about. It's good enough for now. It works. So this is the basic structure of an atom. What we have are protons and neutrons. Now protons, begin with a P, are positive. Neutrons, well, it's in the name, they have no charge at all. So protons are positively charged, neutrons don't have a charge. Altogether, an atom has to be neutral. So if that's the case, then we must have two negatives to balance out these two positives. And we do, in the form of electrons. And they are orbiting the nucleus, like we said, very, very far away. So protons and neutrons, they make up a nucleus. Electrons, they orbit in shells around the nucleus. Only 2 electrons can go into the first shell. If an atom has more electrons, then they go in shells further away from the nucleus. So that is what we call the center of our atom. We call it the nucleus. The protons and neutrons make up the nucleus. This is an electron here. Like we said, they are negatively charged. Altogether, the atom is neutral. Now, when you see an element or an atom on the periodic table, you'll see the symbol. In this case, this is helium, so the symbol is He. And then we have 2 numbers. The bottom number is the most important one. It's going to be 2. This tells you how many protons an atom has. No, that's not a hashtag of protons. Before Twitter came along, that meant number. Now this is called atomic number. This number is always the same for an element. The number on top doesn't have to always be the same though. This is what we call the mass number. Also known as relative atomic mass, sometimes given the symbol AR or just A. This is equals to the number of protons plus the number of neutrons. In this case, we've got 2 protons and 2 neutrons, so it's going to be 4 altogether. So we say we have 4 nucleons. Now this number can be different for the same element. So let's say that we have 2 helium atoms.
They both have to have a proton number of 2, an atomic number of 2, but they can actually have different mass numbers. That's because this helium here has one more neutron than the other one. And that's allowed. They're the same element because they've got the same number of protons. That can't change, but they do have different numbers of neutrons. This helium atom here has 2 neutrons. This one has 3 neutrons. And we call these isotopes. Iso meaning the same, tope meaning element. They're the same element because they have the same atomic number, but they've got different numbers of neutrons, so a different mass number. To draw this, all I'd have to do is add an extra neutron into the nucleus here. Nothing else changes. It's still a helium atom. It's just a different type of helium atom. So you might realise then that if that's the case, then both protons and neutrons have a mass of just 1. We actually call that one relative atomic mass unit. Those of you in second year A-level physics, that's actually equals to 1/12 the mass of a carbon-12 atom. But at GCSE and first year A-level physics, all you need to know is that they both have the same mass. Electrons do have a mass, but we say that it's effectively 0, so we don't factor it into our mass of an atom. In reality, the mass of an electron is roughly 1/2000th of the mass of a proton or a neutron. So don't forget that in order for an atom to be neutral, which all atoms have to be, they have to have the same number of electrons as protons. So you can figure out how many electrons something should have by just looking at its atomic number, how many protons it's got, the bottom number there. If something's got a different number of electrons to protons, it's no longer an atom but an ion. So if something has lost an electron, it becomes a positive ion because electrons are negative. And if an atom gains an electron, then it becomes a negative ion because electrons are negative. Being really pedantic, technically ions can't be negatively charged, but in ionic compounds, you do have particles that have a negative charge and we call them ions. So at GCSE, it's really important that you understand that protons and neutrons have the same mass, and that's 1, and electrons basically have no mass. And also that neutrons have no charge, protons have a plus, that's just +1 charge, electrons have a -1 charge. So you need the same number of each to balance it out in an atom. Now for A-level, you do need to use absolute masses and absolute charges as well. So instead of just +1, 0 and -1, you need to use absolute values. So the mass of a proton or a neutron is equals to roughly 1.67 times 10 to the -27 kilograms. Now in the second year of physics, you'll find out that they have slightly different masses, and it's a very important reason as to why that is. But for now, we can just use this number here, very small. The mass of an electron is even smaller, 9.1 times 10 to the -31 kilograms. Incredibly small, so that's why we say that it effectively has no mass compared to a proton or a neutron. Like we said, this is equals to 1 relative atomic mass unit, or we can say 1 U. Finally, the charge of a proton and an electron, because they're both the same, just oppositely charged. So we'll put plus or minus there just to make that clear. It's equals to 1.6 times 10 to the -19 coulombs. Coulomb being the unit of charge. And we call this 1E. So 1U is the relative atomic mass that we use instead of dealing with these crazy numbers here. And 1E is the charge of an electron or a proton instead of using these crazy numbers here. But we are going to have to use these a little bit later on. I hope that helps you. If it did, then please don't forget to leave a like. And if you think I've missed anything or have any questions, then put it in a comment down below, and I'll see you next time.